Welcome. This is functional analysis, second session on Hahn-Banach theorem. Today we shall look at two special cases of Hahn-Banach theorem, which are again usually not done there, and we will try to understand. And if time permits, we will also look at the first and the most important analytical step towards Hahn-Banach theorem. It all depends upon how fast or how slow we go. Okay, let's get started. So let us recall, what did Hahn-Banach theorem say? It said that if x is a non-linear space, y is a vector subspace, just a vector subspace, no topological condition, and if f is a continuous linear functional on, assume this is a vector space over C or over R. Okay, let us stick to R first. Okay, continuous linear functional. That means what? For all x there exists a C such that this is less than or equal to norm of x for all x and y. Okay, then there exists a G which is from C to R, continuous plus linear, and it's an extension of f. That means G is restricted to y is f. Okay, right. This is Hahn-Banach theorem. What is the simplest case I can think of? Simplest case, of course, is if y happens to be x, right? What is the next simplest from analysis of topological point of view? Suppose y is dense in x. Okay, then it's very easy. Let us assume if f is therefore from to R or even over C, does not matter. Okay, continuous plus linear. Okay, then f is actually uniformly continuous, because modulus fx, or let us say fy1 minus fy2 is less than or equal to C times equal to norm of, it's a linear, therefore f of y1 minus y2, that's less than or equal to C times norm of y1 minus y2. So if I want this to be less than epsilon, I choose delta to be 0 less than delta less than epsilon by C. Then uniform continuity follows, right? And next, this is a very standard result. If you have from a metric space D to Y, this is a dense subspace, and this is uniformly continuous, and this is a complete metric space. Okay, then there is a unique extension G from x to y, so that G restricted to D is f. Okay, right. I'll quickly go through this. There is a video on this extension of uniformly continuous function. You can check it out, or you can also read it from my topology of metric space book. The result is easy. Suppose x is in x, then there is a sequence xn in D such that xn converges to x. Therefore xn is Cauchy, right? F uniformly continuous implies f carries Cauchy sequences to Cauchy sequence, therefore f of xn, this sequence is Cauchy in y. But remember, y is complete. Y is complete. Therefore there is a unique y such that f of xn converges to y. So we define g of x to be y, which is nothing other than limit of f of xn. Okay, now we want to check this is well defined. Suppose there is another sequence yn, and let us say Sn in D, so that Sn also converges to x. Then notice that the distance between Sn and xn will be less than or equal to distance between Sn x plus distance between xn and xn. Okay, so this goes to 0 because of convergence. Therefore distance between xn and yn will be less than delta if n is sufficiently large, right? You understand that? Therefore, okay, there is n given delta, there is n, so that distance between xn and sn will be less than delta for all n greater than or equal to capital N, right? Therefore, if you choose any epsilon positive, then you can see distance between fxn and fsn. Okay, because of uniform continuity for this epsilon, there is a delta, right? Therefore, this will be less than epsilon for all n greater than or equal to capital N. Okay, from this we can conclude fxn converges to y and fsn also converges to y. Therefore, it's well defined. Okay, and then this is continuous, etc., uniformly continuous, all these things. Okay, so this you must have seen in the first course in functional analysis. Please pause. So this is a quick review. I am not saying that I had given a complete proof. This is actually complete proof. Any reasonably good student should be able to complete the details. But you can check my video or my book on metric spaces. But a very special case is proved in functional analysis. Suppose D is a, let us say Z. Okay, this is a dense vector subspace, and Y is a Banach space, that is complete non-linear space. Then suppose this is from D, not Z, sorry, Z to Y is continuous plus linear. Then there is a unique S from X to Y, continuous plus linear, and such that S restricted to Z is T. Okay, remember any continuous linear function is uniformly continuous because T of x1 minus x2 is Tx1 minus Tx2. Okay, that's less than or equal to C times norm of x1 minus x2. I should write this first here and then equal to, right? So this will prove uniform continuity. Therefore, I can apply to the earlier theorem. Okay, and this the extension is okay. Therefore, I put S of x to be, as we did earlier, limit of Txn if xn is in D, Z, and xn converges to x. Then I want to claim S is linear. That's all very easy. Okay, I don't want to waste time. Okay, you can refer to any functional analysis book. So what is the thrust of what the thing? Let's go back to thing. If y in X is dense vector subspace and F from Y to R or C is a continuous linear functional, then there is a unique G from X to R or C which is continuous and linear, and G restricted to Y is F. Okay, alright. So what is the, again quickly, if X is in X, there is Yn sequence, so that Yn converges to X, and define okay G of X to be limit of F of Xn. Why? Because since F of Yn, since Yn converges to X, Yn is Cauchy and F is continuous and linear, therefore it's uniformly continuous. Therefore F of Yn will be Cauchy in RRC, but RRC is complete metric space, therefore the limit exists. This is the basic idea. Okay, please pause, review, proceed. What is the second simplest case? If my X is already a Hilbert space. Okay, most often in functional analysis book, Hilbert space will be after doing nonlinear space, Banach space, open mapping theorem, uniform boundedness principle, etc. After that only they will introduce Hilbert space. So when they come to Hilbert space, they may not talk about Hahn-Banach theorem because Hahn-Banach theorem is already proved. Okay, but it will be very nice to look at this. Suppose y is a vector subspace of x and f is a linear function from y to c. Let us assume the complex vector space, continuous plus linear, right? So I want to extend this. How will I do that? The first thing is, notice that as I did earlier, if y bar denotes the closure of y in x, then this becomes a Hilbert space. Okay, remember y is just a vector subspace, it need not be complete. Okay, but when I take this closure, then it becomes a Hilbert space, right? Therefore, what do I know? Now let's recall the so-called Riesz representation theorem. Okay, therefore there exists, let me call it f bar from y bar to c, such that f bar restricted to y is f. Okay, right? But we can do much better. I will just come in a minute. Okay, therefore f bar becomes continuous linear functional. This f bar. How did I do that? This is just what we did from the first case. Since y is dense in y closure, alright, therefore any continuous linear function on y can be extended uniquely to a continuous linear functional on y bar. Okay, that is done. But now I can use Riesz representation theorem. What does it say? If H is a Hilbert space and if f is a continuous linear function from H to C, then there is a unique x in H, or let us say u in H, such that f of x equal inner product H u for all x in H. Right? You might have seen in finite dimensional inner product space this kind of result. Right? Therefore, there exists a z in y closure, such that for all y in y closure, okay, my f bar of y happens to be inner product of y and z. Right? Now remember, y bar is contained in x, therefore z is an element of x. Therefore I can define g of any x to be inner product of xz. Okay, this will be continuous linear function and which extends f. In fact, it extends f bar and ends f. Yeah? Do you see that? Hahn-Banach theorem is utter triviality in the case of a Hilbert space. Yeah? So enjoy this. Most often books do not even mention this, but it will be very nice to do that. Yeah? In my book on functional analysis, Hilbert space is a special example of Banach spaces, and later when you talk about continuous linear maps, then we talk about continuous linear functional Hilbert space, and I prove Riesz representation theorem there. Okay, therefore before we move on to Hahn-Banach theorem or open mapping theorem, closed graph theorem, uniform boundedness principle or bounded inverse theorem, these things are proved in my book in the first 60 odd pages. Okay, right. Is that clear? So what I have shown now, we have dealt with two simple cases. Okay, what are the two simple cases? One is if the vector subspace y is actually dense in x, then by some other standard result, okay, the continuous linear functional extends uniquely to a continuous linear function on the ambient space x. The second case is where x is itself a Hilbert space and y is some vector subspace. Then what do? We extend a linear functional, continuous linear functional f from y to c to a continuous linear functional f bar from y bar to c. Okay, y bar is the closure of y in the Hilbert space. Therefore, y bar becomes a Hilbert space. In a Hilbert space, we use Riesz representation theorem and we used it. Okay, just enjoy. This is beautiful mathematics. Yeah. Now we are ready to go to the next case. Okay, the general case. Hopefully, I will be able to do at least part of that. Let us. So let us come to the general case now. Now suppose, so again Y is a vector subspace of X is a non-linear space, F is a continuous. Let us assume all these vector spaces are over R to start with, to R, Y to R. This is continuous linear, right? I want to extend it. So if Y equal to X, or if Y bar equal to X, okay, we are through. In fact, this implies this. Yeah. So, but we don't worry about. Suppose Y is a proper vector subspace, right? Then what do I do? Then there is an X in X which is not in Y, right? Okay. Now since it's a continuous linear functional, what do I know? I know that for there exists a okay, the norm of F, okay, this is supremum of norm of F of Y as O varies over Y and norm of Y equal to less than equal to 1 or equal to 1, right? Says that mod Fx mod of Y is less than equal to norm of F into norm of Y for every Y in Y. Okay, this is what it meant by Y is a continuous linear functional, right? Now what I want to show, there is a G from X to R continuous. In fact, I will say it's linear and G restricted to Y is F, and G of X I will claim is less than equal to norm of X into norm of X for all X in X. So what does that mean? I am extending F to G such that the operator norm of G coincides with the operator norm of F. Are you following? I just want to say it's continuous linear functional, but I am actually claiming then the norm of the extension G is same as the norm of F. If you have gone through Riesz extension theorem, you should remember comparing this with that. Okay, there you have a closed set, a continuous real valued function which is bounded. Okay, then you can extend to all of X, which is a completely regular space. Okay, you can extend to all of X such that the subnorm of the extension is the subnorm of the original function. It's exactly similar. Math is beautiful if you don't want to read only for exam point of view. Try to understand all these things. You will also see it's easier to retain the fact, okay, by this kind of comparison and contrasting. Is it clear? So what we want to do is, suppose I will define P of Y to be norm of F into norm of Y. Okay, so what are the properties of P? One, P of Y1 plus Y2, okay, you can see is going to be norm of F into norm of Y1 plus Y2, which is less than or equal to norm of F into norm of Y1 plus norm of Y2, that is equal to P of Y1 plus P of Y2. P of Y1 plus P of Y2. Do you understand this? And second property is P of Ty. Suppose Y is positive, then this is by definition norm of F into norm of Ty, but since it's positive, this is going to be T into norm of F into norm of Y, which is equal to T into P of Y, right? So we are going to look at such functions. So P is called sublinear. That is, if X is a non-linear space and P is a function from X to R, so that 1 P of X plus X1 plus X2 is less than or equal to P of X1 plus P of X2, and 2 P of Tx equal to T times P of X for T positive. Okay, and we call this a sublinear function. Okay, so how do I get one sublinear function? That's what we just now did. So example is, if f is a continuous linear function from x to r, then define p of x to be norm of f into norm of x. This is sublinear. Okay, pause, review, proceed. So let us look at Hahn-Banach theorem in a version. Okay, let X be a non-linear space, P be a sublinear function, X to Y. Okay, let Y be a vector subspace of X, and F from Y to R, these are all non-linear spaces overall. Y to R be a linear functional such that, okay, modulus of f of y is less than or equal to p of y for all y in capital Y. Right? We are not talking about continuity of f. Do you understand this? Yeah? We are simply saying f is some linear function and there is some sublinear function such that. So if it's a continuous linear function, when I want to do extension, what do you think I should do? I should take my p of y to be the norm of f times norm of y. Okay, do you understand? Okay, then there exists an extension of f g from x to r such that g of x, okay, modulus of this is less than or equal to p of x. Do you follow that? So just to make sure that you understand, suppose f is continuous from y to r, okay, then the sublinear function I can define it to be norm of f into norm of y. Right? So I extend this to x to r, namely p of x to be norm of f into norm of x. Notice that this norm of f is only as a, so operator norm of f as a linear function from f to r. Therefore this norm of f I already defined. Where did I define? This way. Okay, this is if you want only with respect to y. Remember that. Okay, so okay, then what does this say? Then there exists a g from x to r such that modulus of g of x is an extension, linear extension of f such that g of x is less than or equal to p of x. That simply means what? Norm of f into norm of x. Therefore it turns out to be continuous also. Do you understand this? Pause, review, proceed. Okay, so we are going to prove the result only with respect to in this notation. So let us recall this. So the simplest case is what I am going to look at. So yeah, I have f from y to r and such that modulus of f of y is less than or equal to p of y. Okay, this is for all y in capital Y, right? Okay, if suppose y is not equal to x, therefore choose an x in x which is not in y. Now let's look at y plus rx. Okay, this contains y, also this contains x. Okay, this contains y and x is an element of this, right? And this is a vector subspace. Okay, notice that this is a direct sum. In fact, when we did algebraic version in the last session, I should have mentioned this is a direct sum. What does it mean? Suppose I have an element z, okay, then I write it as y1 plus, let us say t1x, which is also equal to y2 plus t2x. What do I want to say? I want to say y1 is y2 and t1 equal to t2. Okay, because any element here is of the form some y plus t times x, right? And I want to say this is unique. This expression is unique. That means what? Y is an element of y must be unique. The scalar t must be unique. That's what we are claiming. Yeah, that's very easy, because how will I do? I will look at this y1 to this equal to t2 minus t1 into x. If t1 is not equal to t2, this is non-zero. That means x is going to be 1 by t2 minus t1 into y1 minus y2, and this is an element of y, because y1 y2 are in y is a vector subspace, scalar multiple, therefore x is an element of this, a contradiction, right? Therefore this is a direct sum. Okay, make sure you understand this I should explain in the last algebraic version. See, I thought the time was up and I didn't explain that there. Okay, now how do I extend as a linear functional? As I said, I can do it easily. What is that? I will define g from y plus rx to r by the following. Therefore, if I take any z in y plus rx, then there is a unique y and unique t, so that z is. Therefore, I will define g of y. Remember, I want it to be an extension. I want it to be linear. G of z should be. Therefore, it must be g of y plus g of tx. You understand that? If g are linear, this must happen. But I want g to be an extension of f. Therefore, this must be f of y, right? And this is linear. Therefore, it must be t times g of x. That means to define g on this vector subspace, I only have to tell you what is g of x. If I say, then this function g is defined on y plus rx, and it's well defined. Why it's well defined? Because z has only one representation, y plus tx. Okay, therefore I have to say what it is, right? So let, okay, lambda is a real number, be g of y. Okay, fix some lambda. So I want to define, then I can only define g of z to be f of y plus t times lambda, where z is y plus tx, right? So this you can check, this is linear. G restricted to y is of course f, and g is linear. Why? This is z1 and z2 will be y2 plus 2x. Therefore z1 plus z2 will be what? y1 plus y2 plus t1 plus t2 times x. Okay, and notice that z1 plus z2 will be some y plus tx, but this y must, but I have written z1 plus z2 as this also. By the uniqueness, this must be this, and the t must be t1 plus t2. There is algebra involved, direct sum concept involved. Please understand this carefully. Alright, are you following? Okay, now therefore what is g of z1 plus z2 according to our definition? It is g of y1 plus y2 plus t1 plus t2 times x. But this one, what did I define? I define y1 plus y2 plus t1 plus t2 times lambda. But this is, f is linear, therefore it's f of y1 plus f of y2 plus t1 of lambda plus t2 of lambda. So that is, combine these two, that says g of y1 plus t1x, and this is, combine these two, g of y2 plus t2x, but this is g of z1 plus g of z2, etc. And similarly scalar multiple. So you typically see, by now the teachers assume you have mastered these things and you are a second year MSc student, third semester possibly. So this kind of small things teachers will not explain. It is expected of you. I am doing these things because there may be students who are not very thoroughly understood earlier concepts, so I am trying to explain all these things. If you are very good, you may get bored. I am sorry for that. Okay, you can skip. Okay, right? Therefore, I had extended. So therefore, G from y plus Rx to R is a linear extension. Extension of a very good. But what do I want? I want G of y plus Tx, that is Z, should be less than or equal to P of y plus Tx. Right? For every Z, I want this to be. That is for every y in Y and for every T in R, this must happen. Because what do I want? I want to extend to all of X, but I want to say whether I can extend F to at least to this, so that I will have G of Z is less than or equal to P of Z for all Z in Y plus Rx. Okay. So if I have if I add one extra point, one extra vector to Y, I get a one dimension more. Okay. Then whether I can extend it such that this inequality is satisfied. So algebraically I have done that. But the crucial point is whether I can do it analytically. That is, this inequality should be satisfied. Have you understood that? So what does that mean? This I know what it is. This means f of y plus t times lambda, whether this is less than or equal to. Okay. Now this will I can write as p of y plus t times p of x. I can't write this t unless t is positive. You understand? Or simply write it p of y plus tx. I want to know.